for mobile devices. Qualcomm was nucleated with a $25,000 seed grant when it was a startup company. Now it has 21,000 employees all over the world. That idea, which came out of essentially a mathematics modeling by an electrical engineer, is what started a revolution in telecommunications. Dr. Amar Bose just passed away 2 days ago. And he's pretty much an applied mathematician, an engineering degree. And his work changed acoustics once and for all. And these are all examples of economic impacts of purely basic research. I say this partly to some of the students because there's been a significant shift in demographics within IITs, including IIT Madras, where increasingly there is a significant shift from academic path for a career to an industry path. Both are admirable avenues to pursue, but the point I want to make is that academic path, which some of these examples these people took, can also lead to financial riches. And so please don't overlook that when you make a career decision when you get your BTech degree from IIT. I want to move from local to global. This is the latest data on global R&D funding from Bethel Institute in Columbus, Ohio. This shows leading innovation hubs in the world. Both axes are normalized. So on the horizontal axis, you have the R&D investment in a country as a fraction of its GDP in dollars. So it's normalized by the economy of the country. The vertical axis is the number of scientists and engineers in the country normalized by the population of the country. Okay? So horizontal axis is the economic investment, vertical axis is the human investment. You need both for innovation to thrive. Obviously, you want to be in the top right-hand corner of the graph. The country that's closest to the top right-hand corner is Finland. So if you cannot be in the top right-hand corner, at least you want to be on the right-hand side as much as possible. So let's look at the countries. Israel, Sweden, South Korea, Japan, Finland, etc. The size of the circle relates to the size of the investment. The color of the circle relates to the color of the continent. So all the green colors are the Americas. There are only 3 green circles. Everybody else is too small to be on this graph. The 3 countries in the Americas are US, Canada, and Mexico. Brazil. Mexico is not even in here. So the size of the circles add to the size of the investment. If you add all the green circles, that constitutes about 1/3 of the global investment in R&D, which is 1.4 trillion US dollars adjusted for purchasing power parity. All the orange circles are Europe. So collectively, Europe accounts for slightly less than 1/3 of the global investment in R&D. All the blue circles are Asia, and you can see that India is still close to the left here, and China is here. And this is the size of the investment of India, this is the size of the investment of China, that's the US, and that's Japan. And you can see Germany here. And so if you add up all the blue, and Singapore is here, if you add up all the blue circles, that's about 1/3 of global R&D. But the blue circles are increasing at the fastest rate. Okay? So roughly the world is divided into US, Europe, and Asia. And for the first time, the top 10 Asian countries last year invested more in R&D collectively than the US did. And that trend is an important trend to keep in mind. So with this, I want to move on to explaining why I call it a new era. What is so new about it? There are 4 major demographic shifts that I would like to talk about. The first is global challenges need global solutions. So let's take 2 examples. Climate change. So when they burn forests in Indonesia, it affects air quality in Singapore. So national policies don't matter. If there is pollution in China, that affects rainfall in the US. So doesn't matter where the borders are, everybody is affected. Second is in the area of infectious diseases. 15 years ago, it was believed most infectious disease programs in American universities were shrinking until SARS came along. People realized that an infectious disease is only one airline flight away from anywhere to anywhere. And with now 18-hour flights, you can cover the planet just with one flight very easily, anywhere. So global solutions, global challenges have no national boundaries. So this is the first point. The second point is the borderless knowledge enterprise. So especially with the internet, there are no barriers. Unfortunately, institutions have barriers, national funding has barriers, and national economies have barriers. So how do you create policies that have no borders in them, while you have borders for funding and borders for national rules and laws? But an interesting question is that if there are no borders for knowledge enterprise, and knowledge enterprise governs the world and the course of human events, who will make sure that policies are created, and who will make sure that policies are adhered to, and who's responsible for it, and who will police it? And nobody knows. So this will come to some couple of slides I'll show at the end shortly about some possible avenues. And this is one area where I personally believe that the US National Academy of Engineering has articulated grand challenges for the 21st century. And I personally believe that we cannot successfully find technological solutions unless the engineering and scientific solutions link to the human condition. And so just using a mobile device, you have to take into account the human condition. Whether you predict tornadoes, it's not the technology, it's not the radar technology, it's not the computational modeling, it's how people will respond to warnings about tornadoes that's as important as whether you can detect a tornado 24 hours before it's about to happen. So how do you bring in the human condition in concert with the scientific solution? That's going to be the key. And that's especially important for technological institutions like IIT. How do you engage social, behavioral, and economic sciences with natural sciences and engineering is going to be a critical aspect of it. The third is shifting demographics. And this is a very interesting point. So let me talk about input and output. So let's talk about input. Students graduating from high school and going to university, first-year students, freshmen at universities and colleges all over the world. So last year, the number of freshmen enrolled in all the universities, colleges, and community colleges in all the 50 states of the US combined, and add to that all the students going into university in all the 27 countries of the European Union combined, and add to that all the students going into all the universities and colleges in Japan combined. So world's first number one economy, number third economy, and number fourth economy, all combined together. That number of students equal the number of undergraduate freshmen just in China last year, the number two economy. That's the input. Let's look at the output. College graduates in China. Last year, little more than 20% of all the college graduates in China had their undergraduate degree in natural sciences. Another 20% had their undergraduate degrees in engineering. That's 40%. Take the US. 13% of all the college graduates had their undergraduate degree in natural sciences. 4.5% in engineering. If you take all the college graduates in the US, 1.5% of all the college graduates in the US were women engineering graduates. That's half the population. So this trend is not new. It's been this way for several decades. The question is, the US has such a shortage of scientists and engineers. How did the US become the innovation leader in the last half a century? One of the reasons is that it was the destination for people from all over the world, at least in the last half century. Future may be different. So if you cannot grow homegrown talent, or if there are not in adequate numbers, you have an ecosystem that attracts people from all over the world. There is an economic argument as well. So recent studies show that if you're born in the US, by the time you reach age 22, the cost to raise a child from birth to age 22 is $500,000 in today's dollars. Okay? If you have 100,000 scientists and engineers immigrating after their undergraduate education from somewhere else, top students, $500,000 each in investment, the infusion into the GDP is $50 billion. So there is an economic argument for immigration as well. So these are all the different factors that play into it. It's a very complex thing. There is no simple answer, but it's a very important factor to think about. So that's the shifting demographics. The last thing here, the fourth major trend is the shifting economics. I already mentioned that Asian countries collectively invested more in science and engineering R&D, but most of it is D rather than R at this point. And this is an interesting shift. So I just have a few more slides. Let's look at one of the questions I was asked by Congress was, what is so exciting about science and engineering, and why are you asking for $7 billion for your budget? I had to come up with an answer. So we asked all kinds of experts. So what is so exciting about science and engineering in the year 2013 compared to 5 years ago, 10 years ago? There are many exciting things going on, but there are two major things. You can put all of this excitement into two categories. The first one, this is not my discovery, it came from a number of experts from around the country and around the world. The first is, we are in a new era of observation. So what do I mean by that? On the one hand, we have resolution, reach, and scope of instrumentation with unprecedented capability that can discover new planets billions of light years away using airborne telescopes or land-based telescopes. You also have the technology to drill in 3 kilometers deep into the Antarctic ice to study about carbon capture, pollution levels, fish population, etc. On the other extreme, you can go to a desktop device that a bright young undergraduate student can build for $5,000, where he can impose a force of a piconewton. I want to remind you, pico is 10 to the minus 12 Newton force. You can have desktop instruments that have almost angstrom resolution. Microscopes now, electron microscopes, have sub-angstrom resolution today. So you can go the extra femtosecond time steps. So you can go this extreme capabilities from femtosecond all the way to billions of light years resolution. Add to that the Human Genome Project. Add to that computational science and engineering, where you have capabilities to do unprecedented modeling, whether it's climate change, weather prediction, or genomics, or what have you. Plus you have less than $1,000 for a complete personalized human genome sequencing. So with all of this capability, you have a new era of observation, which is not only limited to scientists, it's available to individuals, to the lay person, the average citizen of the world. An iPad can now generate about a terabyte of data per day. So you can imagine a middle school child carrying a mobile phone and an iPad, participating in a real-time experiment and transmitting the information to a live network of data run by scientists and Nobel laureates, where an individual school child becomes part and parcel of a scientific team on a global scale in a big data project. And this is already being done. A middle school child in Texas, this young girl, helped discover a new planet with a portable device. So these kinds of capabilities exist. So that's the new era of observation. The new era of observation also is giving rise to the new era of data and information. So what is plotted here is, starting in 2012, approximately now, looking to the next 10 years, these are all the big facilities that have been created by funding agencies around the world. So you can see the genomics project around 2012. Blue Waters is a supercomputer at University of Illinois in Urbana-Champaign. LHC is a Large Hadron Collider in Geneva, Switzerland. Climate environmental modeling. And then if you go to 2020, you have the genomics projects, climate and environment, Square Kilometre Array, which is a collective project between South Africa, Australia. India is also involved in this. And LSST is a Large Synoptic Survey Telescope based in Chile, which will come into existence in 2018. So this is how the big data is going to go, at least for large facilities. But this does not include all the portable devices that we have. So if an iPad can generate a terabyte of data per day, look at all the data that's being created. So the problem here is that there is so much noise. How do you extract the signal from the noise? And how do you extract useful knowledge out of this? And how do you make sure that you archive the useful knowledge permanently across rapidly changing platforms? And who will pay for it? Why should NSF pay for it? If somebody else is going to use, and it's a borderless knowledge enterprise. Why should any taxpayer pay for it if everybody is going to use it? So who's going to decide who pays for it? And who coordinates it? Who collects the money? Who distributes the money? Whose laws do we abide by? We don't know. So that means looking to 2024 as director of NSF, I had to decide what do I want to fund now in computer science today so that 10 years from now or 12 years from now, we will have the technology to archive useful information that's filtered out of useless junk, and that's permanently archived across rapidly changing platforms. How do we do that? So that's the kind of discussion we need to have when the pace of change is so rapid. So this is the new era of data information. So these are the two exciting things that are going on. So let me just wrap up with a few thoughts. How do we address this in many different ways from a university? I already talked about how the government addressed it. How does a funding agency address this? I've had a lot of conversation with the Indian government on this over the last few years. Let me give you one example of a collaboration that started, something called SAVI, which I launched in October of 2011. It stands for Science Across Virtual Institutes. We have we have 7 National Science Foundation centers in the US. The 2 of them, one at Brown University in Rhode Island and one in North Carolina, came together. And they wanted to collaborate with leading institutions in India in the area of mathematics, cryptography, and its applications. It turned out that existing National Science Foundation centers could be linked to new activities in places like Indian Statistical Institute, Chennai Mathematics Institute, Indian Institute of Science, Tata Institute for Fundamental Research, etc. So when you bring them together, collectively, they have the opportunity to work together in much better ways. So a $6 million a year investment from the National Science Foundation has been combined with investments from India and others into a $26 million per year investment, which many institutions now share. And this is a win-win situation for everybody. So since October of 2011, now we have 20 new programs that look at this. In wireless communication, we have a program with Finland. Innovation ecosystem. So how do you support it? Now, these are examples of the entire spectrum of innovation. So IIT Madras as a research park, and there are a lot of activities that come from science and engineering into industry through these activities. Here is one model that's practiced in the US by a number of entities. So most of the funding for universities and funding agencies, government agencies, is often basic research, which is the left extreme. If you go to the extreme right, you have commercialization, large corporations. Before that, you have investors, you have foundations. Of course, there's the famous valley of death where most good ideas die. But even before the valley of death, you have small businesses start. And there is a program called SBIR, which now 11 funding agencies in the US have. And it stands for Small Business Innovation Research. And this often helps small companies to get started. So companies like Qualcomm, Symantec, they all started as SBIR companies, and they get 3 or 4 or 5 employees. They get $20,000, $30,000, and then they become multi-billion-dollar corporations eventually if they go past the valley of death. One of the activities I started a couple of years ago was called the NSF Innovation Code. And the idea is to create a virtual network across the US where you take basic research, give a small amount of money for a short period of time, and see whether a scientific idea goes beyond a publication, beyond a patent, into something that has a market value. And it's not the job of the NSF to support it, but it's the job of the NSF just to give a gentle push, and then somebody else will pick it up. And now there are 300 programs that exist along those lines. So the innovation course started with 100 projects in 2012. In 2013, there were 200 more new projects. Now there are 5 national hubs geographically distributed. Most importantly for students, it gives an opportunity. So when they are students, even undergraduate students, have an opportunity to engage with their professors and researchers, with industry leaders. And this is also an interesting training ground, because oftentimes the best scientific idea is not the best business model. And how do you go from a scientific idea to a marketable idea? And so time will tell how successful it is, but the first 2 years have been very encouraging. Another completely different idea, the head of US Agency for International Development is Dr. Rajiv Shah. He and I got together in July of 2011. The USAID, their mandate is to fund developing countries. NSF mandate is to fund only the US. We cannot send money abroad. So we both have to live within our mandate. How do we get the biggest bang for the buck? So we decided, rather than USAID giving money to developing countries, NSF giving money to the US, unbeknownst to each other, suppose we coordinate this. So, for example, USAID gave money to Bangladesh to study pollution in groundwater. The scientists there collaborate with scientists in the US. So previously the money will go separately, they wouldn't talk to one another. Now we'll get the proposals together, we'll evaluate them in a common way, and when we give the money, the condition is that they work together. They already have pre-established contact. So it started with 6 projects in the first year. Second year there were 42 projects. It started with $40 million. Second year it grew to $250 million. So the impact can be enormous. Now you can link it to different countries. So this is another possibility. So let me summarize with a few questions, and I'll leave you with one solution. If you have a borderless knowledge enterprise for innovation, who will develop policies and ensure compliance? Who will organize, distribute, and store scientific information and big data, open access to publications and data? Most importantly, who will pay for it? So the UK government recently announced that they will pay for open access. All British publications will be open access for the world. But here is the issue. England or UK accounts for 7% of the scientific output of the world. Their scientists are not happy that their scientific research funding is being used to pay for the other 93%. Why can't the other 93% pay some portion of it? So that's what the yellow sign asks the question for. So how do you find a solution to this? Who will create policies to protect privacy, confidentiality? This is a big issue right now. And this is going to be very important for the future. Who will develop validation for technology-enabled learning? We have MOOCs and all this. How do we validate it? What is the outcome? Are there large numbers of students enrolling in these courses, but what are they learning? Are they learning? And so these are interesting questions to ask. How will institutions and individuals participate in this global enterprise? So what do we do? So about a little more than a year ago, with input and invitation from the White House, for the first time, we invited the heads of science funding agencies from 47 countries, 48 countries, and 47 came at their own expense. We gathered in Virginia. And we created something called the Global Research Council. This is a virtual organization. No money goes across borders. Everybody pays for their own expense. They assemble once a year. When they come, they don't talk about what they will do. They actually finish something at every meeting. That means they start talking about it a year before. They have a goal. When they meet the next year, they have to finish 2 things. So in the first meeting, held in Virginia, they did 2 things. They created a commonly developed principles of scientific peer review, how peer review should be done. So if the US National Science Foundation wants to work with the Chinese National Science Foundation, rather than saying, this is how I do business, this is how you do business, let's talk about how we will do business together. We can now take a collectively endorsed principles and say, if we want to work together, this is the principle by which we need to abide by, because we both agreed to it already. You don't have to start discussing it fresh. And so that was released, and the second thing was the Global Research Council was formed. And when this was launched, the week after it was launched, Science Magazine asked me to write an editorial, and they wanted 1 sentence that they could use to capture the spirit of it. So it took a long time to come up with this, but this is what I proposed in that. Good science anywhere is good for science everywhere. And so that's essentially a principle for what the Global Research Council wants to do. So the first meeting was held, and here are the principles. Help establish principles of good scientific practices, especially between developed and developing countries, and among research funders, performers, and educators. Advance and disseminate scientific knowledge. Leverage resources across countries without necessarily sending money across borders. And lastly, create a virtual organization. So the first meeting was held, and you can probably recognize another local person, Dr. Ramaswamy. He participated in the first meeting. And this was held in Virginia, and just a couple of months ago, the second meeting was held in Berlin. This was organized by Germany and Brazil, and this had 2 objectives. One was to release the principles of research integrity, which they did, and the second was to create a multi-year process for open access to publications and data. Because this group collectively is in charge of 96% of all science and engineering funding on the planet. So they should be able to come up with a mechanism to pay for it. If they don't come up with a mechanism, we are in deep trouble. So that's the goal. And this group is next going to meet in Beijing. And last year, 110 countries participated in this. Next meeting will be in Beijing, jointly organized by China and Canada. And so our hope is that this is one of the responses to this question. So that's the end of my talk. I want to leave you with this slide. So this was about 3 months ago. I had an opportunity to update President Obama on what happened with the Global Research Council. So this picture was taken exactly at the time when I was describing the previous 3 slides to him. And he looks a little concerned, but he was very happy to hear this. Thank you.